Welcome back to our series on the FFT. We have a few more topics to cover in this series, but before we cover them, we're going to need to be able to access all of the information from a frame of FFTs in the Max domain as a list. So we're going to take a slightly different approach this week. Here's our FFT. If we're going to look at the list, you'll know that the next step to this might be that we want to normalize it, and we've discussed normalizing in the past. But if we can't quite remember how to do it, we know it has something to do with this size. It would be handy if we just had some sort of object we could stick in here to normalize the FFT. So we can do something like FFT normalize. This is a fictitious object, so it'll just come up bogus. But it would be nice if we could just stick something in there that just automatically did the right thing. And after we do that, we'll need to convert it from MSP signals into a list. So we would need something like an FFT list object. Of course, this doesn't exist either, so we'll get another bogus object. And this object right here, this FFT list object, is the one that's going to be particularly difficult to do just with standard Max objects. So I'm going to take a little break from normal FFT and patching world, and we'll talk about creating an object in C using the Max SDK. So if you have some background in C and C programming, you can follow along. If not, you can also follow along just so that you have some awareness of what the process is like. In the next video in this series, we'll come back to patching and we'll be able to use these objects that we're building today. So to get started on our journey, we're going to download the Max SDK. There are a couple places where we could download it. If we just went to the Cycling74 website, there's a link there. If we want the latest bleeding edge version, which may not have made it up to the website yet, we can go and get that from GitHub. So the URL here, github.com/cycling74/Max SDK. And we'll just come here and we can download it. Download a zip. And then we can go find this in the Finder. This is the same SDK regardless of whether we're going to be using Windows or a Mac for our builds. So we go ahead, I'm going to drag this into my Max 7 packages folder. And the structure of the SDK is itself a package, so that's super handy. And I'm just going to work right in here to create our object. We don't need the web browser anymore. That can go away. So to get started, I'm going to go to my source folder. And assuming that you have Apple's Xcode installed, if you're on a Mac, or Microsoft Visual Studio, if you're on Windows, you should be able just to come right in and open up a project and get started. We'll start with some sort of audio object. Let's start with simple MSP. That seems like a good place to start. And I just want to build this project, make sure it works. That way we know there's not some problem with the SDK or with our version of Xcode or something else. So we'll come here. We can see this is the C source code, and we don't have to worry about what it's doing too much at the moment. I'll go ahead and hit the button over here that will build the object. When we go back to the folder here that was the SDK package, we'll now see that an externals folder has popped up, and it contains our external called simple MSP. So if we go over to Max now, we can come here and type in simple MSP tilde, and it doesn't show up. Probably because I need to restart Max. We'll be restarting Max a lot today. Every time we do a new build of our object, we'll need to restart Max. So let's try this again. Start up Max. And now we can come in here and type simple MSP, and sure enough, now it loads. I can option click it to get the help patcher. And as we change the number goes through. This other number gets added to it. It's basically a simple adding object. Great. So we've done that. I'll go ahead and close all of that, and then we'll come back to Xcode. We'll close the Xcode window, come back to our folder, our project, and now we're going to just duplicate this Xcode project and change the name of it. And we'll do the FFT Normalize object first because it's simpler. So we can say FFT Normalize. And then we come in here and change the names of all of these files. So FFT Normalize for the C file, for the Microsoft Visual Studio project, and for the Apple Xcode project. Since we're working on a Macintosh today, this is the one we'll use. I'll double click it and open it up, and we can see that it can't find the simple MSP. That's not the file that we want. So we'll go ahead and drag this file into our project, and then just accept all the defaults. We can delete. So one thing we'll need to do here, because we duplicated a project we already built and Xcode already made it kind of messy, we can go here and we can say manage schemes. And we need to get rid of the old schemes in here. This is kind of like a unfortunate thing about Xcode. Okay, so it did that. Now we can say auto create schemes. It'll create a brand new one. And now we can go ahead and build this project. And when we build it, and we come back over to externals, now it will show us that it built an object called FFTNormalize.mxo. I'm going to come here and look in our source file. And in our source file, we'll just take a quick little tour. First thing we've done is we've included the Max SDK, which are these two lines right here. And then we've included zdsp.h, which is required for all the audio objects. The next little blurb here is a structure, which is how our object's memory is going to be taken care of. And there will be one of these little hunks of memory for each and every instance of our object. We then have prototypes for all of the functions that we'll define below. And we can discuss those as we go along. And finally, we need a pointer to our class. Next, we have an external main function, and this is what will be called by Max when it loads the file from disk. And this function will go through and say, we're going to create a new class. We're going to call it not simple MSP, but FFT Normalize. So change that. And then we'll add some methods to it, or messages, as you may be more familiar with. We'll tie it into Max's system of classes. Then we define what happens every time we create a new one of these externals. And so simple MSP, for example, is going to add an outlet to each one of them. Then we have a function that will be called every time we delete one of these objects or free it. There's a note here that this is not being called because up here we told the class new to use DSP free. Since this isn't being used, we'll just go ahead and delete it. And then we'll go ahead and also delete the prototype if there is one. There isn't one, so that's fine. We have an assist method, and Max knows how to call the assist method because of this add method up here. This is what presents strings in the user interface that pop up above inlets or outlets when you mouse over them. So right now it's doing I'm an inlet and then the number of the inlet. And we can look at that in a moment. Then there's a float input, and this Max knows about because there's a class add method float. And this is assigning the float that comes in from the inlet to X offset, where X here is our structure that we defined up at the top. Then we have a function called DSP64. This is what's called every time you turn on the DSP in Max. Turning on the DSP does a process that we call compiling the signal chain. And what our object will do is it will make a post to the max window saying what the sample rate is, and then it will call object method down here. And what this line will do is it will add a perform routine to the DSP chain, and that means that every single vector that Max processes will call whatever routine we tell it. We tell it here simple MSP perform 64, which is right here. And we can see down here it has in L, which is going to be our input, out L, which is going to be our output, and then the number of samples that exist in this vector. We'll go through each one of them, and we're going to add in L with the value from our struct. So go ahead and compile this now. We'll make sure that it loads and does everything that we said it does now that we changed the name. Here, new FFT.normalize. It shows up in autocomplete. That's good. If we hover over the inlet, I am inlet 0, I am outlet 0, just like we said it was going to do. And then we are going to get some kind of number out of it, which is going to be the, we need to turn on the DSP. And it needs a float that it'll add to that number. Okay? So that is the simple object, and now we can go about modifying and changing it some more. I'll go ahead and save this patcher first, and we can go find that in Documents, Max 7 Packages. We'll put it in the help folder here. We'll make the type a help file, and we'll say this is going to be FFT.normalize max help. So now that we saved it, let's think about what this object needs to do. It's going to need to take data from an FFT object. The FFT object will have a size. So that means we're going to need our object to take real input and imaginary input. And it's also going to need to know the size of the FFT. If we remember from the earlier videos, normalizing is going to take the size of the FFT, or actually half the size of the FFT, and divide all the values from it. The way we did this in previous videos was we would do something like divide by 256. So let's come back over to our C code. All this simple MSP stuff gets a little confusing, so let's just go ahead and do a big ol' find and replace. We're going to find simple MSP, replace it with normalize. We'll do that for the whole file. And I'll build it, make sure that that didn't break anything. And we can come back here. In our new method, we can tell it that we're going to have 2 inlets. We'll do that right here with the DSP setup. We're going to also need 2 signal outlets. So I'll copy this and paste it here. So we now have 2 signal outlets. That's a good start. We're not going to need normal floating point input at all for this object, so I'll delete the floating point method. And we'll delete it up here as well. And we can delete the prototype to it. Because that floating point inlet was simply assigning to our struct, we don't need that number anymore. We now see there's an error down here because this offset is no longer a member of our struct. So let's go ahead and delete that. We also have an error down here in our processing routine because it doesn't know what to do. We'll address this in just a moment. So remember, we want to divide by half the size of our FFT. If we want our object to take an argument, which is the size of the FFT, the arguments to our object can be accessed through this pair. argc is the count of the number of arguments. argv is the actual vector of the arguments. So what we can do is we'll say if argc is greater than 0, we want to make an assignment of the size into our struct of that first argument. And so to access our struct, which is a pointer to a T normalize, we use the arrow, and then we'll need to have a member to hold this value. So let's come back up here. We'll add a member here, and we're going to say double FFT size. Now we can come down here and say X arrow FFT size, auto completion shows us it's there, is going to equal atom get float argv. And then we can say else, which means there's 0 or fewer arguments, of course there can't be fewer, we'll give it some sort of default FFT size. We can just say 512 is the default. So now that this size has been assigned, we can come down here to our perform routine, and remember we're going to divide by X FFT size. It's actually half of the FFT size, so we could say FFT size over 2. Like so. Let's try it out. When we come back to Max, we'll need to quit because this object won't have been updated until Max is reloaded. So we'll just hit save, we'll quit Max, and we'll restart Max. We still have one inlet and one outlet, so that means something didn't happen. Maybe we forgot to actually compile in Xcode. We'll quit Max again, come over here to Xcode and hit build, and then we'll come start Max again. Okay, now we're showing up with our appropriate inlets and outlets. It should be that if we connect this like so, we'll get the same output for both the input and the outputs. It's going to be hard to test this using this FFT right now. That'd be a lot easier actually if we simply used constants. So to test this, we can pop over here and we can generate, using the sig object, we could generate some signal for the real component and some other signal for the imaginary component. And then we can use the number tilde object to see if the results are coming out the way we expect them to. And they're not. Actually, the first number, the real component's fine, but the second number is not fine. And why is that? Let's go back and look at our source code. If we look at our source code, we're saying we're getting the in left from in 0, but we aren't doing anything with the second input. So we can just copy this in, instead of calling it left, I'm going to call this in real and in imaginary. So that would be 1. And then we'll do the same thing with the outputs. So this is going to be out real. Then we'll make another line star out imaginary. And then for our loop down here, we're going to say out imaginary is going to equal in imaginary divided by this. And then we'll also do the same thing for the real component. We don't need this to post to the Max window anymore, so we can clean that up. So now I will go ahead and save this. We'll quit Max again. We'll rebuild. Then we will start Max. Now when I turn on the DSP, we see that we're getting a 0 over here. That's not expected. So how we went wrong is not obvious. So what we're going to do is here where our DSP gets set up, after we've called DSP setup, we can set a flag. And that's going to be in our object structure. Go to ob.zmisc and zmisc. And we can see actually in the documentation that pops up here, one of the flags we can specify is called Zeno in place. And that is what we want to do. So we'll do that over here. Quit that again. Build this again. Come over to Max and start it again. Now when we turn it on, it works. So what this Zeno in place thing does is it disables an optimization. If we just had a simple MSP object with one inlet and one outlet, then there wouldn't be any sort of problem. But in this case, Max is trying to optimize its usage of memory. And because of that, sometimes when you write, for example, we're writing to output real, it's stomping on the memory of this other input because it's trying to share that memory as an optimization. So when you see something weird that's not explainable, sometimes this might be the solution right here, this Zeno in place flag. Okay, so we've done that. We now have FFT Normalize. It would give us the wrong results if the size wasn't 512, but the size is 512. So that is all great. If we change this number to 256 as an example, lo and behold, we get the different result that we expect. We could do some optimizations here. We could cache this value, for example. We could improve the assistance for our inlets and outlets, but I'll just leave all of that as exercises for anybody that wishes to do it. And we can move on to our more interesting case, which is going to be the conversion object that takes signals in and outputs the lists. So we've saved this. I'll go ahead and close it. We can come back to the Finder. We'll find our project, FFT Normalize. We can duplicate it. And now we'll make our new object, FFT List. And again, we'll rename everything. Like so. Then we'll open up this Xcode project. We'll swap out our source files. Get rid of this object, or that file, I should say. And again, this isn't going to want to build right now because this has a dirty configuration in here. So we'll go to Manage Schemes, and we'll just blow away these old schemes and tell it to create a new one. Okay, now we're ready to build FFT list. So we'll go through this file, and I'm going to start by doing a find for every place that Normalize appears. We'll do a replace with FFT list. We'll do this for everything. And one place where it didn't do exactly what we wanted is down here in class new. Okay, So now if I save this, before we go making any changes beyond this, we should just make sure that we haven't accidentally screwed something up. So I'm going to go ahead and build it. Then we'll go see if we can load this up over here in Max new FFT.list. And we can. Brilliant. That's what we want. So let's go back to Xcode now and start figuring out what we need to do. We'll still need to know the size of our list. That's good. When we come down here, I don't see anything that we need to obviously change right away, but there are a couple things we'll need to know. If we're collecting the list and we need to know which values go in which slot in the list, that means we're going to need to use the sync outlet from the FFT. So we're going to need a third inlet to our list object. So we'll make this have 3 inlets. We're just outputting a list, so we don't need 2 outlets, we only need 1, and it doesn't need to be a signal. We'll just let it be a generic outlet, so we can specify null instead of specifying that it's a particular type. Okay. We can leave this little bit here for our default handling of the arguments. We'll ignore this assistance at the moment. This won't change down here. Where the real meat's going to happen is going to be down here. We have our audio routine, and we have a real input, an imaginary input. We don't have outputs anymore. One thing that we do have, though, is we have a third inlet, and that is going to be the index, which is going to be that guy right there. Now what we want to do is, in this routine, we'll want to go through and collect everything into our lists. That means we'll need to have a list to represent our real and our imaginary components. We can come up here to our structure, and we can have those lists. What we'll do here is we can say we want a vector of atoms. Atoms are the native type in Max, so we'll say we have a pointer to some atoms. We'll call this real. We can have a pointer to another list of atoms, or vector of atoms. We can call this one imaginary. Then in our new routine, once we know how many items we're working with, we can go ahead and say that X real is going to point to the memory of the memory allocated for size of a T atom times the number of atoms. We can just duplicate that again for the imaginary. Now, however, we'll also need to make sure that that memory gets freed when the object is destroyed. So we'll have to add a free method. So we'll say FFT list free, and it will take a pointer to our object. And then we will call free on the real and free on the imaginary. We then need to specify that this is our free method up here. Oh, and remember, this is a DSP object, so DSP free still needs to be called as well. And it's important that DSP free in any audio object is the first item to be called. it gives us a warning because the type of X is TFFT list and it's expecting a TPX object. Our first member is a TPX object. So therefore it is safe to cast this like so, and now make the warning go away. Now I just implemented this using malloc and free because it will look a little bit more familiar to seasoned C programmers. Actually, there are alternative functions that can be called that are in the Max API. So we can call sysmem new pointer instead of malloc, and sysmem free pointer instead of free. They're essentially the same, but these are functions defined in the Max kernel, and these are the recommended functions if you're writing a Max external. In this case, there's a casting type. You can see that it just needs a cast here to make the warning go away. And we're casting, in this case, to tatom pointers. So now we have some memory in X real and X imaginary. So let's come down to our perform routine. And let's rewrite this a little bit differently. Instead of a while loop, we can use a for loop, and that might make it a little bit easier to see what's going on. So I'm going to say, I'll have another int called I, and say for I equals 0, as long as I is less than sample frames, we can go ahead and like that. We don't need this up here anymore. Okay, we'll come here and we'll have a double called real, which will be in real I. And we'll do the same thing for the other inputs, imaginary and index. Okay, and when X real, we can go ahead and store this real can go into X real at the index. And we'll do the same thing with the imaginary. X imaginary at index is going to equal our imaginary input. Now it's complaining because we're assigning a double, but this is an array of atoms. So we can't just assign it like this. In fact, we need to use the special functions atom set float. And atom set float is going to take this, which is a pointer to the atom. We'll say plus index will equal real. Okay, we'll build this up. Okay, so the second problem here is saying that there's nothing named imag. I'm going to come up here and look, and I actually spelled out imaginary up here. So I can just go ahead and truncate that up here. And then the other problem is it doesn't understand what T-atoms are because I mistyped it. Okay, so now when I try to build, I fail again. Well, because we changed the name of this and didn't fix it here. And we didn't fix it here. Okay, so the problem with this is that I said the index is a double, but we can't offset a pointer by a double. We actually need to use an integer of some form. Okay, it built. Now the code is still a little bit dangerous here. We aren't doing any bounds checking, so if we sent in some bogus numbers here, it's just going to access random memory, and that's not good. It's going to crash. So we should actually check that the index is in range. There are a few ways of doing that, but one way is that there's a macro in the SDK for Max called clip, or actually it's called clamp. So we're going to take this number right here and we're going to make sure that it is between 0 and 1 less than our X arrow FFT size. That way it's always in the range of 0 to 511 if our size was 512, for example. That way we don't access memory that is not ours to access. So if we build this now, it should build. We're not going to be able to do anything with it. We're just storing these numbers in memory. If we want to get the numbers out, we need some way to get those numbers out. So one way we can go about doing that is we could add a method that responds to bangs. Come up here, we say class add method. C is the pointer to our class that we defined right up here. We're going to cast the function we're about to specify as a method, FFT list. It just doesn't exist yet. We're going to make it up and come back and fill it in. The name of it is a symbol bang, and it won't take any arguments, so we'll just stick a 0 on there and a semicolon. Now we need to define this method. One place we could stick that is down here. So we called it FFT list bang. It's going to receive only the pointer to our object. And here we can do something. We're not sure what yet. But first I'm going to go ahead and copy the signature of this function so we can come up here and stick it up here as a prototype to get rid of this error. The prototype just needs a semicolon. That'll take care of the error there. So what do we want to do in the bang method? Well, basically we want to send out our lists, and we'll need an outlet for the real and an outlet for the imaginary. Remember, we defined those up here in our new method, where in fact we didn't quite do this correctly. One thing we didn't do correctly is we did correctly create an outlet. However, we didn't store the pointer, so we can't actually access the outlet. So that's one problem. The other problem is we need two outlets because we need one for the real and one for the imaginary. In terms of the pointers, let's come up here. We'll make a generic pointer, and this is going to be the real outlet, and we'll make another generic pointer for the imaginary outlet. Then down here we'll say the real outlet is going to equal this, and then we're going to have an imaginary outlet as well. In Max, because of right to left order, we need to actually create these in right to left order, which means we're going to create the imaginary outlet first. Then we're going to look at this error, and the problem is we have to tell it that it's a member of our struct. Okay, back to our FFT list bang. Now we can call a method outlet list. Outlet list, there we go, there's the autocomplete for it. The first argument is going to be our outlet, so in this case, to maintain right to left ordering, we should send the imaginary outlet first. The symbol, because this is a list, is actually, we'll just say null. The number of arguments is going to be the size of our FFT. And then the atoms for the imaginary part are in our struct right here. and then we'll go ahead and do the same thing for the real. Just like this. We have one more problem with our object, but we'll go ahead and try it like this and see what happens. So quit Max again. Start Max up again. And now we'll have FFT Normalize, and to be consistent, we'll go ahead and actually specify the argument to it. Then we're going to hook up that Normalize to an FFT list object, again with the argument, and it properly has a real input, an imaginary input, and an input for the index. And then it has outlets here for these two lists, one for the real and one for the imaginary. So if we did two message boxes for those and hook up an ABC object like so, save our work, turn this on, and we don't see anything. Oh, because we have to hit a bang in order to drive out the lists. There we go. That's a lot of numbers. It's a little hard to verify that those numbers are the correct numbers, but we're getting lists out, and that's pretty great. Let's make this example a little simpler. We could say that the FFT size is going to be 32, which means that the normalize also needs to be for an FFT of size 32, and this list can just be 32 items. Now when we turn this on and we hit the bang, okay, so the sizes are different, much shorter, that's easier. We also know that because we have real input to our FFT and there is no complex input because there's no imaginary connected, that actually the second half of this should be a mirror image of the first half. So we don't need the mirror images. So because of that, we can chop this down even more. We could say ZL slice 16 and ZL slice 16 here as well. Now, when you run this, how did we, oh, I spelled slice wrong. There we go. Okay, so now we get some numbers out of here for our real and our imaginary components of our FFT. So one thing we could do if we want to visualize this and feel like we really know that it's working, we'll make a multi-slider down here. After we've normalized this, but before we turn it into a list, we could run the car-to-pole object on it. Stick the car-to-pole in here, car-to-pole tilde. Like so. And now, when we hit the bang, we can connect this up here. These are all really small numbers, so they're not really showing up very well in this multi-slider. We can change the range to be 0 to 1, which is fine, but still may not show up because those numbers are so small. Oh, they're changed just a little bit. We might want to go ahead and do a little bit of a multiply on this. So we could say something like vexper $f1 times 20 or something like that. And that might show up a little bit better. Okay, look at that. So if I were to hook up a Metro 40, since we're driving a UI object, it might be actually better to use a Q Metro. And then we put this guy over here, Turn that on. We get a little FFT output here. And then if I make it like we can see the differences in this output from the FFT. And we can see our magnitude. And then this over here will be the phases. So that's pretty neat. It's not entirely accurate. And so we need to talk about why that is. We'll jump back over into Xcode. I did a video earlier this year talking about Max's threading model. And if you didn't get a chance to see that or don't know about Max's threading model, I would definitely encourage you to check that out. What's happening is that we have audio performing right here in our perform routine. This happens in Max's audio thread. What's happening with this metro is happening in some thread. We don't know which without looking at our options. In my audio status window, I have overdrive turned on and the audio interrupt is turned off. So that means that this metro is happening, internally it's happening in its own scheduler thread. But because it's a queue metro, it's actually being deferred to the main thread. The main thread is not the audio thread, however. So that means potentially this routine is running simultaneously to the bang method being processed. So what's the problem with that? Well, the problem is that we might be halfway through a frame when this gets triggered. So you have some values from one frame of the FFT and some values from another frame of the FFT. And that's going to be no bueno. So to protect against that, we need to do a little bit more work in our external. One approach to this is we'll have our real and our imaginary, and then we'll make copies of them when they are complete. And then we'll only send the complete frames. So we'll add a real complete and an imaginary complete. When we do this, we'll come down here. Our output from our bang method now is going to be real complete, imaginary complete. And what we're going to do down here is we come through all of these, and after we've written, we're going to say if index is equal to the last frame of the FFT, then we will copy, and we allocated our buffers using the sysmem API, so we need to use the sysmem functions copy pointer from our source, which will be real, to, real complete, and it's going to be size of an atom times the number of atoms. So now only when the frames have been completed will they be copied to the memory location from which the bang is sending them out. Let's go up here. We need to also free and allocate these complete versions. So do that, and then we'll also do it here. Okay, go ahead and we can quit Max, rebuild our FFT list object, and we'll go ahead and start Max back up. We can turn this on, and now we can see everything's happening. Psst, psst, psst. So we could also go ahead and if we get rid of this scaling here that we stuck in, we could come up here and substitute the ADC with a cycle, and then we can change the frequency of the cycle, and as this sweeps upward, we'll see it moving up in our FFT analysis that we're doing here, thanks to our two new objects that we've created. The one other trick that we could do, because this is an FFT, is we could go and if we look at the SDK real quick, there's the FFT info object and its source code is included here. And if I double click this and open it up, we can look in here and it shows us how we can access the information from a PFFT. The way that happens is there's a symbol, gensim here, underscore underscore PFFT tilde underscore underscore, and once we have access to this object, we can use that in other places. If I do a quick search, we get the S thing, which is the object, and that is being stored into this member of our struct. We look at places where that's looked. We can see that here we can find out, is the full spectrum flag turned on, what's the hop size, and significantly we can find out what is the FFT size. So what we could do in our FFT list object or in our FFT normalize object is, instead of specifying this as an argument, if we found out that we were in a PFFT object, we could just use the FFT size that's already specified instead of doing it manually. So that's a nice little trick to add to this object at some point in the future. And now with these tools, we'll be equipped for what comes next. And until that time, happy patching.